In this session, we'll start with various I/O techniques used in 8085 microprocessor. So, as far as the 8085 microprocessor goes, there are four ways of interfacing the I/O devices. How actually the I/O devices can communicate with your 8085 microprocessor, how the input and output devices can be interfaced, can be used, can be can communicate with the 8085 processor. So the first method is simple I/O. So what we have here is there will be I/O devices that will always be ready for communication with the microprocessor. Fine. So these I/O devices are ready for communication with the microprocessor. Uh, so there will be devices that are always in the ready state and can straight away communicate with the microprocessor. So the property of such devices is that these devices are not clock driven. A microprocessor as a result of this, the microprocessor need not wait for these devices to be ready, and we have actually studied the T-ready state. The microprocessor basically keeps on checking which device, which peripheral is ready to communicate, which does not. So in this case, the I/O devices are always ready. They are not clock driven, and therefore the microprocessor does not have to wait for the devices to be ready. Fine. Now, how does the microprocessor communicate with the I/O devices? The communication will be made through programs. Communication is under the control of program. The programmer can basically be able to interface the I/O device with the microprocessor, and you have simple memory related instructions not memory related instructions, simple I/O related instructions that we have studied previously, like in, out, extra, that are in this case used for communication between the microprocessor and the I/O device. So what are the devices that can be interfaced using these methods? We have simple I/O devices like LEDs, switch, extra, that can be interfaced using this technique. So this is the first technique of how to interface the I/O devices with the 8085 microprocessor. known as simple IO technique. And what we see in this case is that the IO devices that will be interfaced with the microprocessor in this case will not be driven, will not be clock driven, and therefore they are always actually ready for communication with the microprocessor, and simple instructions can be used for such interfacing between the microprocessor and the IO device, like we have studied in out extra. And you have devices like LED switches, which are not actually memory, which are not actually clock driven, that can be used for uh, that can be actually interfaced using these methods. So this is the first one. The second one is, the second IO technique is poled IO, also known as status check IO. So what happens in this case is, say for example, this is your microprocessor 8085. It communicates with the device. Say for example, we have an ADC here. Fine. Uh, so the communication lines between the ADC and the 8085, the data lines actually, uh, data bus, we'll have 8 data buses connecting the ADC and the microprocessor, and the status of this device needs to be checked for communication between the ADC and the 8085 microprocessor. So what happens in this case is, the microprocessor checks the ready signal. So the case may be that is ADC is having a clock frequency of some kilohertz, while as this 8085 microprocessor is having a clock frequency of 3.24 microhertz. So communicating, so interfacing this ADC with the microprocessor means we need to synchronize the ADC with the 8085 microprocessor. So it will take time for the ADC because it's running slower as compared to the 8085 microprocessor. It will take time to get ready. So microprocessor basically keeps on checking the ready signal until the external device becomes ready. So this checking of the ready signal is known as polling, and that's why the technique is known as poled IO. So it's an inefficient way of data transfer because time will be actually wasted for the microprocessor. But because the external IO device is clock driven, the microprocessor has to wait for the peripheral to be ready. The IO device in this case is clock driven, and 8085 microprocessor has to wait for the peripheral to be ready. So it's a slower communication method. The IO device that will be used to interface the old IO with the microprocessor will be slow, and it will not be actually ready for communication. So it's a slower method. So there will be clock driven peripherals, and example of clock driven IO devices and ADC that we have shown here, an analog to digital converter. It is a clock driven device. As far as the micro communication is concerned, communication is controlled by the program. So again, you will have to use the programs using instructions. The communication between ADC and 8085 microprocessor is possible. As far as the initiation of the communication takes place, the microprocessor will be initiating the communication, but it will have to wait for some time before, during which it will actually check the status of this peripheral device, keep on checking its status so that it can be seen whether the device is ready for communication or not. So as soon as the device becomes ready for data interchange, the microprocessor gets to know it, and note will be able to the microprocessor will get to know about the status of the IO device as it's continuously checking its status, and therefore thereafter be able to read or write onto the IO device. So microprocessor during this time period remains idle. The microprocessor will remain idle during this time, and it will be polling during this time, and as such a lot of CPU time is actually wasted, and therefore this method of communication is not preferred, and it's an inefficient way of communication between the IO device and the microprocessor. So but you will be still using same instructions like in and out to communicate between the peripheral device and the microprocessor. Fine, so you have studied two so far. Simple IO, it's always ready for communication. It's not clock driven IO device, so there is no time wastage for its in that method. Second method is poled IO. There will be devices that will be clock driven. They will have frequency lesser as compared to a microprocessor. So the microprocessor in this case has to wait for the peripheral device to become ready, and during that time it actually enters the wait state, and the microprocessor is actually idle during this whole time period, so long as the external device becomes ready for communication. And this will not take place only once, it will take place after every communication. The microprocessor will enter a T wait state. So after every instruction it will execute between the IO device and the microprocessor. It has to keep on waiting for the peripheral device to become ready every time. The third method, that is one of the important methods that we need to study in case of 8085 or any microprocessor, is the interrupt IO method. So it's a programmed method again, but in this case the IO device is actually programmed. You will have certain programmed IO devices that will be used, that can be communicating with the microprocessor. So in this process of data transfer, the external device informs the microprocessor that it's actually ready for communication, and requires the attention of the microprocessor. So in this case the microprocessor is not initiating. So how it is different from the poled IO method is, in the poled IO method the microprocessor initiates communication with the IO device, and after that IO device, as soon as possible it is able to transfer the data, it will start communicating with the microprocessor. But in this case what happens, the peripheral device, IO device initiates communication and informs the microprocessor that it is ready for communication. So it will inform the microprocessor that it has some data to transfer and it is ready to transfer that data. So interrupts are again peripherally so these are actually peripherally initiated signals, interrupts, and that actually uh, interrupt the normal working of the 8085 microprocessor. So in this case, the microprocessor may have been doing some other program. It may not be that is not the case in case of polled IO and simple IO. In polled IO and simple IO, since we are telling the microprocessor to receive the data, we are telling it in or out, we are feeding these two instructions, only then it will initiate the communication with the IO device. Here it might be doing some other operations. For example, it was running addition instruction, and suddenly an output device comes and says that it has to transfer some data, so it interrupts the normal uh, procedure, normal working that is taking place at that the microprocessor was actually executing, and will ask the microprocessor to be ready to receive the data from it. So interrupts are actually peripherally initiated signals, and these interrupts are not synchronized with the system clock. Fine. Since they are not synchronized, so it will actually put the microprocessor also out of synchronization. The microprocessor may have been performing some instruction, but it will ask it to hold that instruction for some time, and uh, let the IO device to communicate whatever it has to transfer. So we have actually listed five different pins that are not five, six pins that are actually used in the microprocessor 8085, 6, 7, 8, 9, 10, and 11. Pin number 6 to 11. So we have trap, RST 7.5, RST 6.5, RST 5.5, INTR, and INTA. These are actually used for communication of the interrupts with the microprocessor. So you have trap, RST 7.5, RST 6.5, RST 5.5, and INTR. So these are your interrupts. INTA is actually the interrupt acknowledge pin. So these are your interrupts that will be actually interrupting the microprocessor, and this has the highest priority, and this has the least. That means if say for example your microprocessor through pin number 6, that's actually trap, sends the signal to the microprocessor. Since it has highest priority, so it will be acknowledged straight away. But if the external device uh, communicates to the microprocessor through INTR, that's pin number 10, then since it has the least priority, so microprocessor will actually see whether this needs to be, whether current program needs to be halted, lets it run. Accordingly, the interrupt will be acknowledged by the microprocessor. So you have five different interrupts: trap, RST 7.5, 6.5, 5.5, and INTR. Trap having the highest priority and INTR having the least priority. So using these pins, the external device can interrupt the microprocessor. Fine. Apart from this, the interrupts are also classified into you have two classes. You have maskable and non-maskable interrupts. What are maskable interrupts? You have trap is a non-maskable interrupt. Apart from this, RST 7.5, RST 6.5, 5.5, and INTR, they are maskable interrupts. So preventing the interrupt from interrupting is actually known as masking. So if your interrupt is actually maskable, so these interrupts can be prevented from interrupting the microprocessor, while as trap, that is a non-maskable interrupt, cannot be used, cannot be masked, that means it cannot be interrupted from interrupting. Fine, we cannot actually hold the trap if the IO device communicates to the microprocessor through trap, then it is not possible for the microprocessor uh, to not acknowledge the interrupt. We cannot do anything to not acknowledge this interrupt. While as all the other four interrupts, that's RST 7.5, RST 6.5, RST 5.5, and INTR, they are maskable. That means we can actually be able to prevent those interrupts, those IO devices from interrupting the microprocessor. Fine. Uh, Second classification of microprocessor is you can classify the microprocessor as vectored interrupts, and you can classify them as non-vectored interrupts. So non-vectored interrupts, you have INTR, while as everybody else, that is trap, 7.5, 6.5 and 5.5, RST 6.5, 7.5, 5.5, they are vectored interrupts. What is this vectored interrupt? Uh, in case of vectored interrupt, the address of the interrupt service routine is actually pre-specified and fixed, while as if the address of the interrupt service routine is actually a subroutine that's actually meant for servicing the interrupt. Fine. So if the address is pre-specified and fixed, it is known as a vectored interrupt. If the address is not pre-specified or fixed, it is known as a non-vectored interrupt. So any uh, subroutine can actually be used for servicing the interrupt in case of non-vectored interrupt. So these are your classification of interrupts. So we have studied three IO techniques today: the simple IO, the polled IO, and the interrupts IO. We are not actually done with the interrupt IO. So in simple IO, the microprocessor communicates with the IO device that is simple in nature, is not clock driven, so it is always ready for communication. In case of polled IO, the peripheral device is not ready for communication, and it is a microprocessor that actually initiates the communication with the peripheral device. In case of interrupts, uh, the external device is actually which initiates the communication with the microprocessor. The microprocessor may have been running some other program, but the external signal certainly says no, you have to acknowledge me first, and depending upon its priority, it will be acknowledged accordingly. And also whether it can be masked or not, whether its address is specified or not, it is classified into maskable and non-maskable interrupts, and vectored and non-vectored interrupts. So we have to actually look into the working of these interrupts, how they are actually, how the microprocessor works, and using these interrupts, we can actually also then go on to the machine control group of instructions. Apart from that, we have the fourth IO method, and that is known as the direct memory access, DMA, that we will also take up in a later session. In the next session, we'll continue with interrupts, and we'll see how interrupts actually work, and how microprocessor, how the programming can be done for acknowledging these interrupts. That's all for this session.